Okay, so talking about the selection rules for rotational spectroscopy, let me just back up and get this right here. So here's where rotational energy levels compare to vibrational and electronic energy levels. So that's the energy level landscape, and here are the equations according to for the energy level of this rotational motion. So now let's talk about the selection rules. Light has 1 unit of angular momentum. So if the molecule is spinning, let's say like in this picture, it's spinning like this, and light comes in from the bottom, you might say with the circular rotating polarization, it can be absorbed and cause the molecule to now spin twice with 2 units of angular momentum. Okay. What about delta J minus 1? Well, light could be coming the opposite way and slow the molecule down. So it could be absorbed, but slow the molecule down. Okay. So it could be subtracted from the angular momentum. So since Raman transitions involve 2 photons, what do you expect delta J to be? Since each one of those, looking at the notes, you can see it, yeah, plus or minus 2, okay? But it could also be 0. So the photons of light could be coming in with, sort of 2 units of angular momentum in the same direction, or they could be opposite to each other, where we get 0, or they could be going the opposite direction. So we could have delta J plus or minus 2 or 0. Now, this whole time in this course, and in my teaching of PChem, we talk about symmetry selection rules. And now all of a sudden we're talking about angular momentum. And that didn't sit well with me, because should this be a unique argument for selection rules? It's a clean one. It's very nice. It makes sense. If you have 1 unit of angular momentum in light and the molecule spinning with angular momentum, you could add or subtract 1 unit to the spinning molecule. So it is a nice and clean argument. But my grad student and I were thinking, what could we come up with the group theory or symmetry selection rules for rotation? And we did. So she wrote that up in her thesis, and we got a paper published in Journal of Chemical Education, and she graduated with her master's. So yay for her. That's Victoria. And then we wrote our book together. So very good. So here's our pure rotational absorption spectrum. Look at the wave number axis. Really low energy, right? So the whole thing is roughly 100 to 150 wave numbers. Okay. And we have all of these different spectral lines. So each one of these is a different J transition. So this would be the 0 to 1 transition. J equals 0 to 1. 1 to 2, 2 to 3, 3 to 4, 4 to 5. So all of those. Okay. Remember, this one was at 2B. The next one was at 4B. So from this spot, that's at 4B. The next one was at 6. So from 0, it's 6B over, and then 8, and then 10, and 12. Okay. But notice the difference between these lines is 2B. So in between each line is 2 times the rotational constant. So those transition frequencies are separated by 2 times the rotational constant. And so we get lots of measurements of the rotational constant, which means we have good statistics on the distances or sizes of the atoms, or the like bond lengths and angles in the structure of the molecule. Okay. Now, what's interesting, when we did our 1D particle in a box, and you can go to the text and read the transition dipole moment integral. So we did the transition dipole moment integral, and we got a pretty complicated solution. I asked you some questions about that on your homeworks and so on. It was equation 4.8 in the book, and it showed for the absorption spectrum for a particle in a box. Well, particle on a ring, when we did that one, and I didn't ask you any questions about that one, but when we did that one, the transition dipole moment intensity did not depend on the box length. It did not depend on the box mass or anything. It was a constant. So we finished that integral, and we got a constant value. It was 1/4. So that was our conclusion from the 1D particle in a box. But we look at this spectrum, and we don't see a constant intensity, right? Well, one of the reasons we don't see a constant intensity is because we have the Boltzmann distribution, okay? But this spectrum is completely modeled by just the Boltzmann distribution. So it does support our conclusion that we got from the 1D particle, it should be particle on a ring actually, PR, 1D PR, that the intensities all have, relative to each other, the same probability. The only difference is the Boltzmann population. And so the Boltzmann distribution has this G piece, G of J. So that's this piece right here. That's the degeneracy. And then it's got the e to the x piece. Well, this is going to go up with quantum number, right? As J goes from 0 to 1 to 2 and so on, it's going to go up. So this is the G, the degeneracy piece over here. If I can find my pen. There it is. So the degeneracy piece is going up as the quantum number goes up. So that means there's like one chair for J equals 0, because 2 times J is 1, 2 times 0 plus 1 is 1. So there's like one chair there, but then you go to J equals 1, now it's 3 chairs, and then 5 chairs, and then 9, or 7, let's see, 7, 9, and so on. So there's more chairs for the molecules to sit in at the higher J values, and it's statistical. If you come into a room and the front row has 1 chair and the second row has 3 and the third row has 5, and then you look to see the general population of those, you're going to have more people in the third row than you have in the first row, because there's only 1 chair in the first row and there's 5 chairs in the third row. Okay, so statistically, we're going to have more molecules in the J equals 5 state than we have in the J equals 0 state. Okay, so that's why the intensity goes up. But eventually, we don't have enough temperature to get to those higher levels. And so because we're at a finite temperature, the Boltzmann exponential decay takes over. And so we'll have a maximum here, a max value that depends upon temperature. Question? Yeah, and so we can take all these spectra. Let's say we picked the intensities and the frequencies of all of these, then we could model them with the Boltzmann distribution in Excel. So we could have our intensities here in this column, and then we could have our Boltzmann distribution in this column with the temperature up top, and then we could take the differences between those intensities and have a column of differences. We could square them so they're all positive. We could sum them together, and then we could take the square root, and we could have the root mean squared difference of these two columns. And then we change the temperature until those differences are small. So we would reduce those differences by changing the temperature. And when we get to a minimum of those differences, we have the temperature of the gas. Now that's thermodynamics, but we're using spectroscopy to do it. Now I want to ask you guys a question. Do we want to have that piece in Excel where we determine the temperature of a gas as part of our project? Because we're going to do a rotational vibrational spectrum, and we're going to have, it's more on the thermodynamic side, but it's using spectroscopy to measure the temperature of a gas. And this is how we would measure the temperature of our atmosphere. Do y'all want that to be part of the project? Raise your hand if you think that's neat and want to do that. Okay. Okay. The ayes have it. We have 5 to 4. Okay. It's just a temperature analysis using the Boltzmann distribution of the intensities. And of course, I'll have a video to show you how to do it. This one right here is at room temperature. Yeah. And this is carbon monoxide. Yeah. Yeah. And so we have that many excited states. You know, we're at, so J equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, 17, 18, 24. I can see 24 levels. So we have excitation, measurable excitation to J equals 24 at room temperature. Only one is the fundamental. Remember we talk about fundamentals? This is the fundamental. What are all these others?
hot band.
There you go, hot bands, exactly. Thank you. All right, so now we can do Raman spectroscopy with this too. So we know about the Raman effect, in and out photons, inelastic scattering. Since we have so many hot bands in rotation, it's very easy to get anti-Stokes, where we have an excited molecule hit with a green photon, blue photon comes out because it's dropping down 2 levels. And so we have lots of anti-Stokes in the pure rotational Raman. This does not require a dipole. And so this is what we get. We get a Rayleigh line, and then we get the Stokes and anti-Stokes lines. So this is what we see here in the spectrum. We would have this big line in the middle, which is the Rayleigh scattering line. And then we have the anti-Stokes lines and the Stokes lines. Okay. The advantage of this is that fluorescence is always redshifted. So if that laser line gives us fluorescence, this would be a fluorescence signal. But there's no fluorescence on the anti-Stokes line. So this has a 0 background by definition. Anytime you can get a 0 background technique to work, that's what you want, because you're fighting fluorescence on the Stokes side. It's very easy to get anti-Stokes with pure rotational Raman, but for like vibrational Raman, you got to have an excited state, and these vibrational levels are thousands and thousands of Kelvin, so it's not real easy to get anti-Stokes vibrational Raman. You can in combustion, so for jet fuel, like jet engines, and you're looking at the light coming, or the molecules coming out of the back of a jet engine, then you have vibrational excitation, and you can probe with a laser, and you can get anti-Stokes vibrational spectra out of like combustion analysis. And then we get to vibrations, okay? So that's a single vibrational mode. Molecules in reality are like going in all their vibrational modes. So here's the harmonic oscillator model, like Hooke's law here, and it's a parabola, okay? And this is a molecular potential energy. This is just for a diatomic again. We're looking at this, you've got the internuclear separation, and you've got this harmonic oscillator model. The polyatomic vibrational motions are determined by this projection operator in the character table, like we've done fairly recently. They have a known symmetry, and these different 3n-6 vibrations are called normal modes of vibration. So if we zoom in here at the bottom, we see that this is what it looks like with the vibrational wave functions. They don't exactly look like particle in a box wave functions, but they're kind of close. It's not exactly a sine function. You see that it in the very center it looks like a sine wave, but it tapers off a little slower at the outer edges. Okay. There is equal spacing in the energy levels, and so that's V equals 0, equals 1, 2, 3, 4. Notice the particle in a box was n squared, so it went up by n squared. The rotational energy levels were J times J plus 1, so J squared. So it went up by J squared. V is going to just be equal spacing in energy levels. They also look like the particle in a box symmetries. Notice this one is even. If I put a mirror here, it looks to the left and the right look the same. If I put a mirror there, left and right look the same but are opposite sign. Okay, so that's odd. So we have even and odd, just like we have in the particle in a box. And so we're going to have, at the very minimum, the same selection rules that we had with the particle in a box, as at a first approximation. Okay. Now let's look at this region where the harmonic oscillator, this parabola is the harmonic oscillator model. Okay. This part right here is the anharmonic. So this anharmonicity is this one right here, right? I'm trying to show this line right there. So we're looking at this region where they deviate. Okay. And so here's what the energy levels there. Now I've added some things last night just to kind of emphasize that the anharmonic levels are closer together. So I'll put the quantum numbers here. I labeled it 0 for both. But look, here's the V equals 5 state for the harmonic oscillator. Look how much higher it is than the V equals 5 state for the anharmonic. You see that? Yeah. And then the 10, why does this one so low? You know, this is 10 here for the harmonic oscillator. Look at how far down 10 is. It's like 30% error in that case. If you were to, like, say the V equals 10 has this energy, but because of anharmonicity, it's down like 30% of what you predict. So this decreasing energy level spacing, can we understand this from the particle in the box? I think so, because look how wide the box is for the yellow. And if I'm going to make the box wider, the energy levels are going to get closer together. And in this case, the box is changing all the time as we go up. But still, as it gets bigger and bigger, the energy levels get closer together. So the intuition of the particle in a box should still help you. If I've got a bigger box, the closer energy levels. Yes? The yellow one is purely theoretical, is harmonic oscillator. The red one is what we would see with a bond stretch. Like as we stretch the bond and pull it off of the other atom, then that's the curve that we see. Because see, as they get close, this is the equilibrium distance. So as the atoms get close, the electrons spill out to the outer part of the molecule, and the nuclei start to see each other, so they repel. So that's why it's steeper than the harmonic oscillator, because of the repulsion. Can you see the red line is steeper? And then over here, as we pull on it, the electrons spill to the middle, and then as we pull, then the electrons start to go with their individual nuclei, and so then there's less of a bond, and so we see that it gets weaker and weaker, and then finally you just have the dissociation energy. And so also, as we go up in vibrational excitation, you could think as sort of the equilibrium bond length is maybe halfway between the limits. So the harmonic oscillator has the same bond length no matter how excited it gets. Okay, but the anharmonic system, the bond length lengthens as you go up in excitation. So you would have a bond length, so you would have a R0, and you would have a bond length for V equals 1, so you call that R1, and you have a bond length for V equals 3 and 4 and 5, so you would have lots of bond lengths, and depending upon the vibrational excitation. So that's a little strange, okay? So an excited molecule would have a longer bond length than an unexcited molecule. And so when we're talking about bond lengths, sometimes we use RE. If we extrapolate these bond lengths down, we hit this RE, the equilibrium bond length, which is really the bond length at the minimum of these wells, where both of these anharmonic and harmonic meet and are the same. Okay. Okay, and these are the dissociation energies. If you're taking the dissociation energy from the very bottom of that curve, you would use dE, but D0 here is from V equals 0. So it's not DO, it's D0, because it's from V equals 0 to the limit. Okay. So here's our harmonic oscillator energies. And then here's what it depends upon. And I was asking y'all questions about this in your projects. These are good equations to know, specifically this one. Here's the vibrational frequency, and here's the force constant, and here's the reduced mass of what's being moved. So if there's a lot of mass moving, you have a low frequency. If there's a tiny mass moving, like a hydrogen on something, then it's a high frequency. Here's the strength of the bond, this force constant. You have a triple bond, high frequency, single bond, low frequency. So these play into each other. K is the force constant, and mu is the reduced mass. For a diatomic molecule, the reduced mass is really easy to calculate. And then sometimes, in order to calculate that anharmonicity correction, instead of trying to model that shape, which we can with a Morse potential, but it's not perfect, it doesn't match experimental well, We just do a polynomial fit to the experimental data. Okay, so a polynomial that you're familiar with, the x term and then x squared and x cubed and so on, just a polynomial fit. But in this case, our x is our vibrational quantum number piece. So this piece right here is our x. I'll just type x, and then this is our like x squared term and our x cubed term. You see what we're doing? Just a polynomial fit, okay? And then so I use those x's just for your familiarity with like a polynomial, a equals ax squared plus bx plus c, that kind of thing. But I don't want to leave these x's on here, see, because we have a term in front of here, this anharmonicity term for the quadratic piece is x as a anharmonicity correction term. So like this piece is the same here, and then we just add in this little factor xe. And since the harmonic oscillator levels are too far apart from experiment, we subtract this. So we correct them down to match experiment. But as V gets high, this correction overcorrects. And it'll actually turn to where you're exciting the V quantum number, but it's going down. So that doesn't make any sense, right? You've got from V equals, say, 7 to V equals 8, now the energy is lower. That doesn't make sense. So we need to add in a cubic term. And so we add in a cubic term to keep it going up. And so this correction piece is YE. We don't have a lot of YE constants for molecules, but for some of the diatomics we have them. So you can find these in the tables. But it's always this prefix piece is always HC nu, and then we have an XE and a YE. So transitions, here's the transition equation. So from 0 to 1, our quantum numbers are plus or minus 1 for V. So we can put 1 in here for V and subtract 0 when V equals 0. And notice how the 1/2s cancel. And we have 1 minus 0, which is 1. So our transition equation for plus or minus 1 is just the vibrational frequency. That's kind of weird. It's nice, but it's weird. So this is the frequency at which it's vibrating, but that's also the frequency at which the peak shows up when you do the transition. Okay, so they're both. It's the vibrational frequency of the molecule, so the CH is vibrating like that. But if I want to go from V equals 0 in that vibration to V equals 2, where it's vibrating twice as much, the difference is also 3,000 wave numbers. So it's just how it works out. 1 to 2 is a hot band due to thermal population of V equals 1. And anharmonicity, this is where it opens up. Anharmonicity allows plus or minus 2, plus or minus 3, plus or minus 4, and so on. So we do have overtones. 0 to 2 is the first overtone. 0 to 3 is the second overtone. That's confusing because you don't see a 1 anywhere in here. Okay. 0 to 1 is the fundamental. So 0 to 2 would be the first overtone, the first available overtone. And then jumping by 2 levels, going from 0 to 3, actually 3 levels, that's the second overtone. The first overtone frequency, if they're equally spaced energy levels, it's going to be 2 times nu. And so that's what it is here, 2 times the vibrational frequency. That's the overtone. But if we correct for anharmonicity, it's going to be a little bit less than that. But if you're looking at a tiny little peak in your spectrum, you got a vibrational spectrum or a Raman spectrum, and you see a little peak, and you're like, gee, I wonder what that is. If you take that frequency and cut it in half, and you have a really tall peak, it might be an overtone of that one. So like you got a peak at, let me try to do the math here, 2,800. Tiny little peak at 2,800 wave numbers. And you're like, I don't know of any of my functional groups that should absorb at 2,800. What could that be? You look at 1,400, half of that. You have a really tall peak, it might be an overtone of the 1,400 peak showing up at 2,800. Okay. So everybody understand what I'm saying? Yeah. Okay. So yeah, we can look at all these different kinds of samples, solid, liquid, gas. but IR is very sensitive, so the thickness of the sample can overwhelm the signal pretty easily. So if you look at liquid cells for infrared, their spacing is in the microns, like 2 or 3 microns path length, if you're doing pure liquids. And so you have to really, not have thick samples or anything. Raman has trouble with colored samples because it uses visible lasers typically, and you can absorb that visible laser and heat it up and burn it. And then the rotational structure is not resolved in liquids or solids. So for rotational spectra, you need to have a gaseous molecule. You have to have a gas phase molecule. And so comparing IR and Raman, as you saw with your molecules, looking at the Raman and the IR in your projects, you could definitely learn some good information. So Raman's a 2-photon process. We've covered this quite a bit. Anti-Stokes only happens with excited molecules in really hot situations. And so here's the FTIR of automobile exhaust. So we have CO2 and water and a little bit of carbon monoxide. But we see that this CO2, this asymmetric stretch is in the infrared 2349. It's A1U, it's a Z motion, it's along the Z axis of the molecule. If I've got symmetric stretch, that's Z squared, that's going to come in as A1G, that's going to be only Raman active. Who was it? Was it you that did the rule of mutual exclusion? Yeah, that's what this is. This is a molecule that has an inversion center. So all inversion center molecules will have this rule of mutual exclusion. So this symmetric stretch is only Raman active, and the asymmetric stretch is only IR active, and the bending motion is also only infrared active. Now we have some other bands up here. These are combination bands of the CO2. Okay, and we can learn about those later. So here's the acetonitrile. Does acetonitrile have an inversion center? So acetonitrile, let's draw that. CH3, CN. No inversion center, yeah. You have a methyl group over here and a CN on it, okay? What is the point group, if we could just quickly spit that out? Well, it's the CN, yeah, it's linear, that's right. So since it's linear, it's all on the Z axis. C3V, yeah. So the CH3 part looks like ammonia, and then we have a carbon and a nitrogen directly above the carbon here. And so they're all on the axis, and so they don't change anything in terms of with twofold or whatever symmetry. There's still threefold symmetry. And so keeping the atoms on the axis hasn't changed it. So it's just like ammonia in terms of the number of symmetry elements it has. And so it's a C3V molecule. And look at all of its different vibrational modes. 4 of them. Well, first of all, how many atoms do I have? 4, 5, 6. 6 atoms. N equals 6. So 3 N minus 6. Okay, 3 times 6 is 18. Minus 6 is 12. And vibrational modes, I only have 8. So what's going on with that? Pardon? Degenerate? Yeah, degeneracy of this one here. These all count for 2. Okay, so like XY. So we have in that E, we have an X vibration and a Y vibration. We could have the symmetric stretch or the asymmetric stretch where you have the 2 times 1 CH stretch minus both the others, and then we don't use that first CH stretch and we have the others 2 moving up opposite of each other. So we have those kinds of things. The bending motion of the CN on top, it can bend along the X-axis, it can bend along the Y-axis. Okay, so that's an XY. So that's also going to be E. So we have all of these. CH3 rock, the CCN bend, the deformation of the methyl group, which should be like the rocking motion of the methyl group, and then the deformation stretch. So those are the four degenerate modes that move perpendicular to the axis, and then we have the modes that move symmetric with the axis. The CC stretch, the symmetric deformation. Let's see, that's the umbrella mode. Okay, the CN stretch, and then the symmetric stretch of the methyls. So that's this one, all three methyls moving at the same time. So can you picture all those now after your project? Maybe? Which one is confusing you, if any? Which one? This one? Okay, so I'll change this one to well, here's a CH3 rock. This would be like the this motion here. So the rocking can go this way or that way. Okay, this one where they're scissoring on one side or going yeah. So I can't do this because I only have two arms. Um, picture the CH coming out of the back of my head. This is one deformation. Okay, okay, and then the other one is just that guy moving. Okay, so kind of like the wag of the one CH or the scissor of the other two. Yeah. So I'll do that. I'll put wag and scissor. Oh, that's a wag, scissor, and rock. This one's rock. We got that one. And then the stretches. That would be the two stretches like this, and that one's stretching while these are compressing. So that's in this direction, and then going in that direction. This one doesn't move, and these go like that. So they're going this way and that way. Okay. So there's two of those. So we would say the asymmetric stretch. Okay. Here's benzene. So benzene has 12 atoms. So 3 times 12 is 36 minus 6. We should have 30. And let's count them up. 1, 2, 3. We got 10 here. And then how many does this count up? This looks like 20, but these all count 2. So that gives us 30. So we have all 30 here. What do we see in terms of the rule of mutual exclusion? Yeah, we have some Ramans that are not IR, we have some IRs that are not Raman, and then we have a lot of modes that don't interact with light. So in the character table, these are rows like B2G and B2U that don't have an X squared, an XY, or YZ. They don't have an X, Y, or Z single, unit. They don't have anything that would allow scattering, Raman scattering, or direct absorption to cause that mode to jump. Okay. And so when you simulate the spectrum for benzene, it's really simple. For the IR, you have this peak, and those three, and one down here. So we have 5. And for the Raman, we have 1, 2, 3, 4, 5, 6, 7. 7 peaks in the Raman. And yet there's 30 vibrations. Okay, so that I went really fast. I thought that I would have to squeeze this in. Okay, but that's okay. There's time. We'll pass out the tests.